something has a given voltage V. That voltage you can think of as an electrical pressure. That's all it is. How many are Emmys in here, arrow? You know the pressure at the head of a pump, right? There's a pressure difference that's just like it is here in electrical pressure, not mechanical. Follow me? That's the analogy. So this is the voltage source. Another symbol for a voltage source can be this. If that says V equals 12 volts, it's assumed DC, and DC stands for direct current. It means nothing changes with time. You all know batteries are not time-varying output voltages, right? The way you get a time-varying phenomena is change the load or change the resistance it's hooked up to, and then you will get a different value of current, and we're going to get to that. So that's a battery. Now the next thing are resistors that you know about. Resistors look like this. This is just the schematic drawn, R. That's all they look like. And the units of resistance are ohms. Typically 10 ohms, that's the symbol, 20 ohms, 5K ohms, 20 mega ohms. You're familiar with the term K in milli, right? Or M for mega. Mega is 10 to the 6th, right? K is 10 to the 3rd. You all familiar with that? Micro is 10 to the minus 6. Pico is 10 to the minus 12. All those things we'll use, those, I guess, prefixes, but this is just something. That's a resistor. Then after that, we get into something called Ohm's law. And it says this, and I'll explain. V is equal to I times R. I'll try to keep it as simple as possible at first. So, if I have a voltage source, V, and I connect a resistor across it, R is the resistance, the result is a current that flows from the positive to the negative terminals, I, and I is simply V over R based on this equation. V equals IR, that means I is V over R, right? If I have two of the three things in this equation, I can solve for the other. Do you all see this, class? Now this is basic physics, correct? The analogy is in mechanical engineering and in aero, I wish I was better with industrial, is that if this was the pressure in a pump, this would be the restrictive force of the pipe, or the actual resistance, what do they call it, fluid resistance of the pipe. And the current that's flowing there would actually be the flow rate. You all follow me, class?
Yes, sir.
And that's all really we're talking about here. The analogies are direct and they're clear. So now, chemical engineers, I'm not going to get into chemical processes. Chris Roberts and I would have some fun talking about the analogy for that. But fundamentally, it should make sense to you. All right. Now, so how many remember seeing that back in the day in high school physics and college physics? If you haven't seen this at least about 100 times, then you really probably are in the wrong class, because that's overkill by a factor of probably 100. So next, we put them all together and we start talking about things that are a little more complex. Not a lot more, but a little more. So now we talk about how do we actually add and find equivalent resistor when they're in series or parallel. So first I got to show you what series means. If I have my battery here, and then I have some resistor R1 and some resistor R2 back to here, and I want the current through here, we can get it. And some of you already, mechanical engineers, they see through these problems very quickly, in my opinion, when I've taught this. They think immediately like this is like a couple of pipes that are connected in series, Well, the resistance goes up as the sum of the resistances, right? They know that. They know that that current I right here is simply V over R1 plus R2. Y'all follow me? Now, I can prove that in a lot of ways, but it is true. And in general, if you want an equivalent resistance for any number of resistors that are in series, you just add them up and replace it. Now, what do I mean by in series? Now, there's probably different ways for me to explain this, but it means the same exact current flows through both. Y'all follow me? There's no way this current I flows through here and doesn't flow through there. It's an impossibility. Do y'all follow me? Think of it as an incompressible fluid. Whatever flows down is going through both of them. They're in series. They may have a different voltage, but they have the same current. As a matter of fact, you could say if you have any number of resistances, R1, R2, R3, dot, 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 R to the N here, and you wanted an equivalent resistor here, it would just be the sum of R sub I from I equals 1 to N. Y'all follow me? And that should make sense. Does it make sense to everybody? Mm-hmm. All right. In the back there, you guys still okay? All right. Now that's in series, that's the same current. There's also a way to connect resistors in what's called parallel, where not the same current, but same voltage is actually going to go through. And this would be in parallel. If we had, matter of fact, let me just show you the resistances. I'm not going to draw the whole circuit. If I had a resistance here, R1, R2, and say R3. We're going to do it this way. And I want an equivalent resistance. Y'all see that if I have these things and I put a voltage here, I'm going to do it this way. I put a voltage here, V. You see the same voltage. Oh, I didn't mention it. You see these dark lines here? You can think of those representing wires. They're equal potential surfaces. It just means that the connection can be thought of as a perfect conductor. Do y'all follow me on that? You know what wires are, right? All right, so that's what I'm doing here. I'm just showing that this is, these three would have the same, because if you look at this plus and minus, well, there's no, when I say a perfect conductor, it means there's no electrical voltage difference at any point. So this really is plus V, this is plus V, this is plus V. This is minus, this is minus, this is minus. Do y'all follow me? They got plus or minus between them. So you can see, and it's pretty evident, that if I put a V there, well, the current here would be equal to V over R1. The current here would be V over R2. And the current here would be V over R3. Or I could say the net current, I total, is just V times 1 over R1 plus 1 over R2 plus 1 over R3, right? You agree with that? Nothing fancy, right? I mean, does everybody agree with me, first of all, class? All right. I just pulled out the V. I just added this plus this plus this. That's the total I. Well, then I can say that since back, if we want to replace that with a single resistor, think of Ohm's law, V equals I times R, right? That means if I take 1 over this, I would say that V here over I total would be 1 over R1 plus 1 over R2 plus 1 over R3. And you can see that that is equal to R equivalent. I'm going to make it simple in a second. Y'all with me on this? The only thing I've done is say, all right, I've got 3 resistors. They're all in parallel. What's the equivalent resistance of that? This is it. It's 1 over the first, plus 1 over the second, plus 1 over the third. Y'all follow me? It is that simple. In general, if you have any number of resistors in parallel, so if you wanted the equivalent of something where you had R1, R2, R to the N in parallel, the R equivalent here would be equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus dot, 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 1 over Rn. Y'all follow me? Nothing tricky about that either. So now, the next thing is, well, what if you get combinations of them? And what if they're not drawn nice and straight and clear like this? How do you go about analyzing it? There's probably a lot of schools have thought of that, but what I try to do, if all else fails, I'll use colored pens to actually indicate all the points of equal potential. And anytime you get anything between like a blue and a green would have the same voltage potential, and I could find out what it is that's in parallel and replace it by a single resistance. Here I'm going to give you some problems. I'll bring that out.
Don't raise the last thing. Don't raise that last thing.
Over there?
Yeah.
Okay. All right. So now we do a problem and we see how we go about doing it. This is going to be simple. I'm going to have a voltage. This is going to be a real voltage. And I'm going to have 5 volts. Then I'm going to have a resistor of 10 ohms here. Then I'm going to have a resistor of 20 ohms here. Then I'm going to have a resistor of 10 ohms here. And a resistor here of 10 ohms. And the question is, what is the current I flowing there? Y'all follow me what I've drawn? Think about it for a second. It's very easy. Just think about it. How do I go about solving that? I want I. What do I need to do? By the way, the default units are ohms. I don't put ohms all the time, but if I needed a different unit, if it was kilo ohms, I put a K there, mega ohms and amp. Y'all follow me? So with nothing, assume ohms. So how do I figure out that current? Anyone? Kirchhoff's law. I didn't even tell you what Kirchhoff's law was. You're ahead of the game. I mean, go ahead.
Well, I see this as like 2 loops. I don't know how you would do this with.
You've had some of this before. Anyway, you could. He's way ahead. You don't need Kirchhoff's law for this one. What can you do? What I'm really trying to show you is how to think about problems and simplify. Anybody in the back? Anybody see something we could do to simplify this? If we want I, what do we really want? We want the resistance is equivalent, don't we? Isn't that right? How many see that? Or how do we get it? You guys
use parallel?
Say again?
Do you use parallel? The 10 and the 20 parallel?
Well, this. What, are you talking about these two?
Yeah.
They're not in parallel, are they? The voltage here is not across these two. As a matter of fact, they're anything but parallel. But there's something in series. Does anybody see it?
Well,
the only 10 ohms are.
We see these two are what? 20 ohms in series, correct? How many see that? I got a 10 and a 10. I can replace it with a 20. Do you agree?
Yes, sir.
Show of hands if you do. All right, so I'm going to replace it by a 20. And I'm even going to put it this way so you can see. So that's a 20, right? Now, think about it. What do you notice? I drew it this way on purpose about the 20s. Anyone?
They're in parallel.
How many see they're in parallel? 20 in parallel with 20 would be 1 over 20 plus 1 over 20 is 2 over 20, 1 over 10, 1 over 10 is 10. Do you all see that? Here's a trick. Identical resistors, if you have them. If you have 2 of them, you take the value of 1, divide by 2. 3 of them, take the value of 1, divide by 3. N of them, take the value of 1 and divide by n. You all hear me on that? It's a nice little trick. So here I've got 2 in parallel. You can do the math on it, it works. All right? And I can see that this could be replaced by 10. Do you agree with that? So I'm gonna. All right? We don't need to go Kirchhoff. I never try to use a bigger tool than I need to drive a nail in or to solve this kind of stuff. I try to keep it as simple as possible. Don't use anything you don't need to. So now finally, what's the current? What do I do with these last 2, anybody? Now I'm boring, you're ready to start throwing tomatoes at me. But what do I do? Add them up, and what are they? Just 120 ohm, right? So make that 20, and now what's that current gonna be?
1.4.
It's always the pressure or the voltage, 5, right? Divided by the resistance, 20, or it's 1/4 of an amp. You all see that? How many see that right there? How many felt that that was a problem they could solve on their own? Give me a show of hands. I hope you all do, because that's right up your alley. It's very basic. This is something you get in high school. When I was in high school, I had electronics. I think when I was a sophomore, we had things like this, and they worked. And they would develop a much more complicated stuff, but they would start right here to make sure everybody sees it. Okay. Now, one other thing, and I didn't say this yet, but you know, that's just current, but something. I mean, we got mechanicals in here, we got industrials, we got chemical. There's probably a few other types of engineers in here. One thing we all like to know about is power, right? How much power is being supplied, how much power is being consumed. And I want to use this to talk about how much power is being used by this circuit. When you have a resistor R, and a current I is flowing through it. Now these are steady state, time invariant values. Then the actual power that is being dissipated or used, however, whatever term you want, the power used is equal to, and I'll just tell you, normally they say if a current I enters the positive terminal V, right there, power is V times I. Now I'm going to make it simple for you. You see how I put a plus and minus there? And here with Ohm's law, I don't think I did that, but in general, when you have a resistor R, and there's a current I through it, that gives rise to a plus to minus voltage V equal to I times R. You'll notice the position of the plus arrow here has to do with the current's entry point. Y'all follow me on that? It's the side the current is entering. So from that point of view, I can replace V right here with I times R, or I can get I squared R is the power. And the units of power are watts, by the way. Y'all know that? Power is watts. I mean, I don't go to English units, I leave it as watts. So then after that, I could also say it's equal to V squared over R, right? That's also in watts, that's power. So here's the deal with the resistor. If you know the current through the resistor, you simply square that value and multiply it by R if it's a DC current, you have the power. If you know the voltage across the resistor, you simply square that and divide it by the resistance and you have the power. Do y'all follow me? So for this one, how much power is being used by this resistor, dissipated in the circuit?
1.4.
It doesn't matter how you do it. How are you going to do it?
I did V times I.
Sure, V times I is probably the easiest, so it's 5/4 of a watt, right? Or 1 0.25 watts. Do you all agree with that? Anybody have an idea? Give you a feel for this. How much power does a hairdryer burn up?
Yeah, in the thousands of
You
watts.
can go for about 1,000 to 1,500 watts is typical, isn't it?
Yeah.
I mean, I think it's typical. I suppose you can get them as low as you want, but that's a typical range, all right? The wall voltage has 117 volts RMS, call it 120, right? So what would that make the current if you had 1,000 watts? Think about it. Let's make it nice and simple. Hairdryer's using 1,000 watts. Wall voltage is not 120, say it's just 100 volts. It's a DC equivalent, it's called RMS, root mean squared value. It's really 117. Call it 100, right? So how much current would be there? About 10 amps, right? Now 10 amps, I'm trying to give you a feel for this stuff, because you're going to be engineers in the field. 10 amps for a hairdryer, yeah. 500 amps for a hairdryer, all right. Should, in your gut, it should be one of these things that you check things with, especially as you go up in management, because you're going to get all sorts of bizarre statements made to you. My graduate students have made bizarre statements. Well, I got this for the value. Really? That's amazing. That's more than the mass of the earth. They'll come up with that, and they don't have they don't have anything that's a check, if you know what I mean. Don't they teach that in ME, in Aero? You need a check to make sure you don't, blow up a plane or something like that. It's the same thing in EE, because you can burn the building down and hurt if you dissipate too much power too quickly. All right, now we'll do another one. Can anybody, out of curiosity, tell me when it's supposed to start raining around here?
4 or 5.
I hope they're right, because I do not want to be here, even with an umbrella, because this stuff's supposed to come in hard and heavy, I think. But I guess it'll be later, that bad stuff. Come on. All right, so now I'm going to do another one. I'm going to show you about things like grounds and stuff like this, but I want to do one more to make sure at least we feel good about this, all right? So here comes another one. Think about it before you answer. This is going to be 10 volts, 10 ohms, 20 ohms, 40 ohms, 50 ohms, 30 ohms, 20 ohms, you all see it?
What's the one on the far right?
This is 40.
Okay.
They don't have to be this nice and squared. They can be at angles. I'm trying to make them square so on the back, you guys won't be wincing at it, all right? And please, next time, move down further. I think you'd find it a little easier to see. Even though I can't, I mean, I have sat back there and tried to read stuff that people put up like I'm doing. I don't know how you can, but I guess there are people with a lot better eyes. Now, what I'm after, and this is the kind of stuff I throw out you on quizzes. Everybody asks me some form of the question, what kind of questions will be on the quiz? Here's one, based on what we just said. So I would ask for something like the current through the 50 ohm resistor, and I'd ask for the total current I. You with me? Two different questions, and you're to do this using your knowledge of how to basically figure things out. So how would you do this? Let's start, before we get up to that current flow in there, how would I find the total current flow in there? How would I simplify this? Please take a good look and think for yourself, force yourself to try to say, all right, this is the test. Suppose this is for money. Suppose you figure it out, you get $1,000. Maybe money doesn't motivate you. How about, I don't know, I think about free meals at Vendatories for life, something like that. I can't think of anything that'll motivate some people. They've got everything. Anyway, go ahead. What are you gonna do? Were you gonna say something? Yeah.
Just start with the 50 and 40.
What she's doing is the absolute right thing. Forget about this question for now. She's gonna say, just replace them with the 90, right? And now, I'll do it over here. So I'm gonna replace these two with the 90 ohm, right? And then I'm gonna put the 20 right here. And then I'm gonna put the 30 here. And then I'm gonna put the 20 here, just so you can see it. And then put the 10 here. Okay. You're doing good. What next? Let her answer. She's right. No, you can do it. Yeah.
Parallel, or
Yeah, right. Which one's in parallel?
the 20 and 90.
How many see the 20 and 90 in parallel? I drew it that way on purpose. So that's going to be what? Well, that's not that easy to see, is it? It's what? Really, it's 20 times 90 over 20 plus 90. I don't even know the value.
16.36.
Thank you. So I like calculators. 16 point what?
36.
36 ohms. I on purpose chose, I'm going to just leave it like that to debug it. Y'all with me? Thank you very much. Who said that? Okay. Why don't you take the next step? What do I do?
The 16.36 and the 30 in series.
How many see that? Far back? You guys got it? So I'm just going to add this up and make that 46, right? All right. We're getting down to the point. How about this side of the room? Anybody? What the next step is? The 46.36 and the 20 in parallel. Can you give me that?
13.97.
What is it?
13.97.
Man, you're quick. 13.97. All right, finally, what do we do at the last step?
They're in series.
Add them up, right? Just add the numbers, right? You agree? So that's going to be a total of 23.97. And lo and behold, that's the answer to that, right? Y'all hear me? Now, from that, what do we know? Let me just show you. First, let everybody get a handle on it, what I just said. Y'all follow what went on just now, right? Some of you are way ahead. You're bored by this. I know that. In these courses, I get very, very bright people. I get some of the brightest people I ever encounter in these courses. You're from all disciplines, ME, industrial, aero. I don't think civils have to take this anymore, but you come from everywhere and you get some extremely bright people. And some people that have been immersed in this stuff more than me even, because of whatever technical background they have. I mean, mechanicals especially with this electromechanical energy scavenging stuff, they're in it, especially if they've done a lot of co-op work. But some of you are not, and you're a little unsure. You're not. Those are the people that need to work at this the most. The people that really got it don't, but the people that are a little bit unsure, they're not totally given and understand. So anyway, y'all agree that's the actual equivalent resistance here, right?
Mm-hmm.
So now my next question is, what is the current? How do I get this current? And I'll just call it IS for source. What would it be? Anyone? 10 over the actual 23.97, right? And that would be in amps. The units of current are amps. Do you all agree with that, class? Now that gives me the current. I want to show you how to do this problem. Now once I have that current, do you notice that all that current has to go through the 10 ohms? How many see that? All right. That means we can find the voltage across that 10 ohms, can't we? How many see that? I didn't even get into the sum of the voltages around a closed loop of zero. It's Kirchhoff's voltage law, but I'm just showing you commonsensically how you figure it out. So do you agree that if I wanted the voltage drop here, or the voltage change, it would be just that current times 10, right? Y'all agree with that? So it'd be 10 times whatever that is, or 100 divided by 23.97. Can you provide me with that answer?
Yeah, the amperage is 0.417.
The voltage.
No, the amperage, and then.
Oh, okay, all right. This is 0.417 amps, and then multiply that by 10, so it's 4.17 volts. So I have a plus to minus of 4.17 volts there. Do y'all see that, class? Now here's where I introduce the next concept, but I'm trying to do it in a way that you've got the question on your mind, now I'm going to answer. So the question would be, well, how much voltage remains from here to here, right? Legitimate question? And here's how we get that. We use the thing, I'm gonna first expose you to Kirchhoff's voltage law. This is Kirchhoff's voltage law. It simply says the sum of all the voltage drops around a closed circuit is 0. And now I'm going to tell you how to get the voltage drops across a closed circuit, because you don't know that. But I'm going to show you, and I'll do this thing in a way that's meaningful. And then we'll get back to this problem if we have time. Hopefully we will. So, if you have a resistor, another resistor, bless you, another resistor, and a voltage source, V. And I'll call that V source. I'll call that VR1, VR2, VR3. I've done this, I've just put a couple of resistors, 3 resistors in series with a source. I didn't give any values to resistance, but I did show you the direction the current's flowing, from the positive to the negative terminal. That's the way current flows. All right, always goes from the positive to the negative for a single source. And then I said, well, the voltage on the first terminal, voltage will always be defined as really, I'll just do it for this one, it would be I times R1, and the plus is here. Y'all see what I've done here, class? I'm not trying to make this in any way, shape, or form tricky. So when you talk about this law, the sum of the voltages being 0, here's how this works. You start at any point in the circuit. Usually I start at the lower left-hand corner, right there. Then I move clockwise, and every time I go from a negative to a positive, that's a voltage increase. Y'all follow me? Whatever was on this side became greater by that value, Vs times with a plus sign. Y'all follow me? Likewise, when I go from a positive to a negative, it's a voltage reduction or loss. Do y'all follow me? So around this circuit, the equation would be Vs, if I started here, be an increase. Then it would be a decrease right there. Then it would be a decrease right there. And a decrease right here. That's the sum of the voltages around the closed loop is 0. Y'all follow? Now the reason I said that, and this is intuitive to you, I'm making it more than it needs to be. I could just as well say that if I wanted these other voltages here and here, I could shove that value on the other side, make those positive. Do y'all see that? Taking that to the other side would be plus R2. This would be plus VR3, right? Would be equal to this. But my point is this. I took the source voltage and I'd subtract VR1 if I wanted the voltage between here and here. Are you with me? I'm moving a little faster because I got 5 minutes. So now what I can say is this. Please watch this. I know I've got 10 volts here and I've got 4.17 volts here. So the actual voltage remaining between here and here will be equal to 10 minus that value. How many see that? Right? Because if we start here, we get an increase of 10, Then we get a decrease of 4.17, and that means the remaining voltage has to be plus to minus that way. Do y'all follow me? Again, how many see that? Okay? You're squinting your eyes. Can you not read my writing, or is it not big enough? You okay with it? Oh, no, not you. It's right there. I try to read faces even with masks to see it. If you can't read my writing, then it's on me, all right? And I can make it bigger. All right, you good with that? Back to this. So what's remaining here? 5.83 volts. Remember, that's what I wanted originally. Y'all remember that? All right, now what do I do? Well, I'm going to show you this. There's several things we could do, and I'm going to show you a trick. Y'all agree if I have this many volts from here to here, I could say that that 20 was in parallel with 90, and that was equal to, I forgot what it was, 13 point something? You did that before.
16.3.
16. We had an equivalent value of resistance here, right? Y'all remember that? I could take that equivalent and add 30 to it, right? And then I could divide that by what? Divide that by, or divide it into 4.17 to get, sorry.
Or wouldn't you have the 20 in parallel too?
Yeah, but I'm just worried about the current coming down here. Because if I get the current down here, I know that current's made up of this current and that current, right? But see, if I get the current flowing here, this is my way of reasoning. Y'all agree if I have the voltage here to here, and I want just the current flowing here on this outer part, I could sum these two together, put them in series, then in parallel for an equivalent resistance of 16 point whatever it is, right? 16.67 ohms. Put that in series with 30, then I could say 4.17 divided by that series combination would be the current, correct? Now once I had that current, then I'd have the voltage drop here, right? That current times 30, right? Then if I took that voltage drop and subtracted it from 4.17, then I'd have a volt.
0.83?
Say,
Don't you mean subtracted from 5.83?
see that 4.17, that's from here to here, right? Can you see that?
I thought it was,
No.
I thought you said 5.83.
Oh, I'm sorry, 5.83.
Okay, good.
That's on me, you're absolutely right. Subtracted from the 5.83 from here to here, thank you. Subtract whatever the voltage is there from that, and then what do you find out? That's the voltage that remains here, right?
Yes, sir.
Then if I wanted the current through there, I'd simply take whatever that remaining voltage is and divide it by 90, and I'd have the current. How many see that? No hands right there in the middle section. Do you understand what I was trying to do? What I'm really trying to do is figure out the current through here. Once I have that, I have the voltage drop there. Once I have that voltage drop, I can subtract it from, as you said, the 5.83 to see the voltage remaining. And I know since that voltage is across the 20, it's also across the 90. I divide by the 90 to find the current, because I wanted the current through there. That's one way of doing it. I don't want to burn you with that one. Am I out of time?
It's exactly at time, 45 seconds.
All right, now I want to tell you this. The reason I was doing that was to work up to show you a trick, how you can do this without doing all these steps. And the way is by finding out how voltages actually divide across resistances in series, and currents divide across resistors in parallel. I'll pick that up next time because I'm out of time. Did you understand? If you understood this lecture, raise your hands so I can understand. Okay, good.